Good morning. All right, let's see. So, hi, I'm Jesse Wilson. I work on a bunch of different products and features and things at a company called Square in Waterloo. And today I'm going to talk a lot about HTTP. I've been working on this library called OkHttp, and although I moonlight as an Android developer, I've been working server-side for several years, and I feel like I've got a bunch of different things where working on client, working on server, I've learned a lot about how to make HTTP work, how to make it not hurt, and how to make it fast. So here we go. What is HTTP? It's a bunch of stuff. Probably most interestingly is it started out not being able to do anything other than web pages. The first versions of HTTP, there was no way to express anything other than here's some HTML. And it grew from web pages into web applications, and then because we had web applications and XML RPC, or XML HTTP request, HTTP basically started to become an API layer. And today, we think of HTTP as the way that our mobile apps talk to our servers, but it's become pretty much all the networking we do anywhere on our computers. So one of the examples, something that's relatively new, is there's something called DNS over HTTP, and it's kind of like a weird inversion where the very first thing you need to do to get a URL is to make an HTTP request, kind of backwards. And so pretty much all the networking you're going to do from now going forward is likely to have some HTTP thing underneath. And so some of this will seem rudimentary. I'm going to try and go into not just how the protocols and APIs work, but actually how to go with the grain and make HTTP work really well for you. This is what an HTTP request looks like. It's got a URL, some headers, and a body, and then the response. Pretty similar. There's a status, some headers, and a body. And you'll see here that it's just a plain text protocol. And so if you take if you go on your Mac or Linux command line and you say brew install NC, NC is called netcat. It's just it's almost like telnet. You can just make raw network calls to servers. And so here I'm making a netcat call to square.com, port 80, there's no TLS here. And I can just type in an HTTP request. And this is very satisfying because it just shows you how little abstraction there is between this is just how basic what your HTTP client is doing for you. So if you think that OkHttp is full of really smart stuff, all we're doing is just translating the things you give us into these strings. How rudimentary, all right? So it's grown a lot up in the years, The first very, very first implementation of HTTP was in 1991. I was 10 years old. That might seem like a very, very long time. In the age of the internet, it feels like HTTP has been here forever. The internet lasted a long time before it existed. And basically in the last 28 years, HTTP has been basically taking over the internet protocol by protocol. The only real interesting thing is that in 1997, that's when the big popular version of HTTP happened, HTTP 1.1, and that lasted for a extremely long time. There was just a very, very, almost 20 years where the protocol didn't change at all, and there was a lot of things changing underneath it or above it. There's in the internet in 1991 looked like Yahoo, and in 2015 it looked like Instagram. So a lot of things changed over in that period. What does this title mean? HTTP in a hostile world? Basically, there's just lots of things that is making it difficult for us as application developers to just get our jobs done. So we want to make our programs correct. It should be obvious, but there's a lot of things that are little traps. We want to make it ready. I'm going to go into these things through the whole presentation, but ready, I mean both available and fast, secure, and the last thing I'm going to end the talk with is just a bunch of new stuff I'm excited about. So we'll start out, we're going to build something that's like correct. How hard could it possibly be? We've assembled, the smartest minds. We've spared no expense. So first off, we're going to just make an HTTP request. Here our user is going to say, hey, send key for $20 for pizza and beer. And our bank's HTTP server is just like, nothing. And then, send key for $20 for pizza and beer. And of course, what happens, of course, is like the bank says, successfully transferred $40 to Kiefer. So this is the universe that we application developers live in. The technique we use to fix this problem is called idempotence. And it's a very, very fancy word for basically a concept of repeat the request, don't repeat the repeating a request won't repeat the corresponding action. There's lots of different things between your application and the money moving or whatever that will trigger repeats. Users could double tap the send button, your application layer could retry, your network code could retry, gateways retry. So despite the fact that like the retrying or the double tapping is invisible, there's lots of different reasons why a single request could look like two. And so I've got this beautiful alliteration implementing idempotence by identifying intention. This is just a recipe to avoid this like double send problem. And I feel like this seems like it should be basic table stakes, but I'm constantly seeing apps that are sending $40 for pizza and beer. And I assume that a lot of our applications in this room have this mistake. So I just want to give the recipe. Generate a universally unique token. So this is just, find some library to give you a random number. 128 bits is enough. Write that intention to your SQLite database or something, and then when you process the action on the back end, persist the identifier so that you can tell if you've received the request a second time, to not duplicate it. One thing we do on our backends is we just put unique indexes on these things, and that is awesome because it's just like as soon as you put the unique index, you don't even have to really think about it in the application layer, it just happens for free. There's one of my favorite examples of idempotence not being implemented correctly is there was a bug in the Starbucks card, and the way it kind of worked was you'd go to Starbucks and you'd swipe you'd pay with your Starbucks card, and they would debit your balance, but it wasn't atomic, and so some enterprising hackers got the same Starbucks card, they duplicated it 4 or 5 times. And then they went to like 5 different Starbucks and paid for the same thing all simultaneously. And Starbucks basically debited, you could spend $500 with a $100 Starbucks card if you were fast enough and you raced it enough. So idempotence, we think of it potentially as just something that's like saving the user from sending an intent twice, but it's also useful for basically making it so your coffee shop, poor Starbucks does not go broke. So next thing I want to talk about is just like we're designing API contracts, and we're going to do a pizza order in JSON. The server is going to send an HTTP 200 if things work. This is kind of like what this looks like. I assume we're all building APIs like this. Everybody building APIs like this? Yeah? So make an HTTP request to the server responds, your pizza's on its way. This is like the fundamental purpose of the internet. And we build this, we ship it, pizzas are being delivered, everything is great, and then sometimes something goes wrong. And so we talk, the client developers talk to the server developers, and we say, we need to support errors. And typical way is now, if it works, we'll send a 200, but if it fails, we'll send an HTTP 500 with the failure info in JSON. Server says, oven's too hot, something like that. And so, exact same flow. The client is expecting to parse this JSON. Everything's working healthy, and then there's this like thing that is invisible that comes and stomps on us and makes our applications crash. And this is called Middleboxes. And so, when things are working normally, conceptually, my app is talking to my server. Usually it's like, somebody on the same floor of me in the same buildings, maybe somebody sits on the other side of the desk as me, is building the same backend for this. And conceptually, it's my app talking to my server. But in practice, there's actually just layers and layers of potential situations where there are boxes in the middle between your devices and your servers that are intercepting your traffic and rewriting them. This could be something where you're like, on day 0, we know it's a direct connection, a direct IP address or something. But as applications grow in complexity, these middle boxes find their ways in your system. Here I've got imagine a Google Cloud HTTP load balancer, but there could be all sorts of different reasons. And what ends up happening is if the pizza server melts down due to a pepperoni malfunction, what could happen is the middle box is now what I'm talking to. And so when I think I'm talking to my server and getting HTTP 500 from my server, I could be talking to some box that's standing in for my server. And this is something that we as mobile application developers need to be aware of and design for. Conceptually, your client talks to your server, but there's this invisible infrastructure, and it can fail to be invisible. So how do we write code in this world where sometimes we're not actually talking about what we think we're talking about? If you review the HTTP status codes, the two interesting ones are there's 200, everything's working. There's the 400, which is it's the mobile developer's fault. You screwed up, you made a bad request, the URL's not really there. And then there's the 500 ones, which are the server's fault. In the place I'm working on in backend systems, it seems like the 400s and the 500s are symmetric, and it doesn't really matter if we do a 400 or 500, it's still a failure. But what I've learned, and becomes really important, is that distinguishing whose fault it is really important for deciding who has to wake up in the middle of the night and fix things. And so I work on, server to server, API server sometimes, and so somebody changes something, they break something, and it's not necessarily always obvious which team should get paged in the middle of the night. And so 400 says the team that made the request gets paged in the middle of the night. They have to wake up. They have to, sign on to the internet at 2 in the morning and fix something. 500 means it's the other team. And if you get this right, you wake up the right person, and you've got one less person who's grumpy. And if you get this wrong and you page the other team, they're not just grumpy at the system failing, but they're grumpy at you. And they're going to wake up, and they're going to be like, it's Jesse's fault. I have to wake him up. I'm annoyed that I had to wake up. I'm annoyed I have to wake up Jesse. Jesse's not saving anything. So this stuff is significant. And then the other thing that these status codes do is they remind us whether or not we're talking to a middle box. And so when we are talking to our own servers, they're going to have predictable content types. We're going to have both the content types we send and the content types they return. If it's HTTP 200, then it's very unlikely that our request has been intercepted in some meaningful way by a middle box. But if there's any other status code, you have to be defensive. You have to say, oh, it's a HTTP 500. I can't just take the response and parse it as JSON. It could be an HTML failure page. There's a bunch of different libraries that sit on top of your HTTP client to make building applications faster, easier, more declarative, more structured. Retrofit is a good one, and you basically write an API that you write a Java interface that looks like maps a REST call to a network call, and it's pretty awesome and really powerful. And there's cool new things coming in new versions of Retrofit, like magic coroutines. One of the things that we're migrating towards on Cash App is this thing called gRPC, and gRPC is an alternative to Retrofit, basically. And so instead of this server team building APIs and then the client team looking at those APIs and squinting and trying to write the right Retrofit interfaces and then testing the back and forth and making sure everything works and making sure we didn't typo the field names, with gRPC, what happens instead is you declare a service declaration in Proto, and it looks something like this. And then the gRPC compiler magically builds an interface for you. And so the server team and the client team bind to the exact same code. You don't have to do this thing where the server team exposes the interface, documents it ideally, and then you have to sort of reverse engineer, build a client, and hope the two line up at runtime. Instead, with gRPC, you build one declaration, and then clients and servers integrate magically. If you're doing images, there's a new library called Coll, and it just like, you point your image view at a URL, and it just does the rest of the work. And then if you're testing your code, inside of OkHttp is this helper library called MockWebServer. Your code isn't really, it isn't really correct until it has tests. I really feel like testing is the conclusion of building correct code. And so with MockWebServer, you basically get to enqueue what you believe to be representative test cases, representative responses that the server would send you. And then you can make HTTP requests against effectively localhost. And it's a real web server, but it's a real web server that's designed for unit testing. And it starts up super fast. There's no like big, complicated, weird configuration. You don't have to write any XML files to run MockWebServer. You just put that in your test case and get off to the races. And one thing I really also like is you can build this test case by recording real test traffic in the wild, and then potentially get your server team to code review the MockWebServer test cases, because they'll be able to say, actually, you're like missing this important field. Like this is showing the server team speaking their language, basically. I'm going to give a live demo of the process of like recording an HTTP request. First thing in the morning, doing a demo is super dangerous. Can everybody see this? The font sizes are a little bit terrible. This program is called Charles, and it's a paid app. It's available for Mac, Windows, Linux. And what it does is it lets you man in the middle any pair of HTTP calls. And so for my example, I've got my to-do list app. I'm working on this project, and I just want to say, like buy shaving foam, right? And I'm going to put that in my to-do list, and I've hooked up Charles to man in the middle the communication between this app that I don't maintain and its server. And then I can go into Charles and just look at the HTTP calls it's making. And in this case, there's an HTTP call, and I can see somewhere in here, it's like, buy shaving foam. So what's really awesome about this kind of tool is you can just like see the network calls that you're making. And this works just as well between an Android app and a server as a Mac app and a server. But if you really want to understand a protocol, for me, I have to see it. Like working in the code is good, but this is where this is my happy place. So that tool is called Charles Proxy. There's a bunch of like similar and equivalent tools, but Charles is the one I've been using for a long time. I really like it. It observes all your HTTP calls, and you'll notice it intercepts HTTPS. That's like crazy magic and really powerful. And like, I just did it on that Mac app without having to configure anything really. So now we're going to build our application. We're going to make it both highly available and highly performant. And the first way to build anything highly available is with redundancy. Building redundant things is hard and annoying, and you need to build complicated, eventually consistent, weird distributed systems problems to work across multiple data centers. But redundancy is also excellent because it gives your effectively server team the ability to make pretty catastrophic mistakes and keep going. You like, oops, we like deployed a bad code change, and now we have to flip from the West Coast data center to the East Coast data center. One thing that's relevant here for mobile developers is that if your server team is running services on two coasts, and at Square we have 4 or 5 data centers in different locations, your HTTP client has to help you to find the right data center. So it's not sufficient for like the West Coast data center to go down. We also have to make it so that the client will automatically fail over to the East Coast data center. Connectivity is a lie. There's this like sort of like thing that we think about as abstraction, which is that I have a connection to the server, and that this connection, the connection itself exists. But it's really just a leaky abstraction. There's no real like physical TCP connection. Instead, what's happening is I sent a message to the server, and the server responded, And I could say that message in the past completed, and so we had effectively the ability to exchange messages, but that's not predictive of the ability to send future messages. And so any API you see that like tests whether you're connected to the internet is probably just like wishful thinking, and the only way to really be sure that you're connected is to make an attempt and see if it works. And it's not just like your app that fails. Bell and Rogers, we love them. Backends also fail, and when we're building our applications, the easy part is getting the happy path working. The fun, complicated, unpleasant part is making sure that the application works even as things are melting down. So first, easiest way to make sure that things work even if connectivity is unavailable is just to avoid making requests. Doing push versus polling is a really easy way to limit how many requests are being made. And then I really like building your application so that your local data has enough to render your application. This also makes your application really fast. Nothing's worse than like getting a notification that says, something has happened in your important app, and you tap on it, and then it has to make a network request to tell you what just happened. You tap on the notification, you're like, you have my attention, and then it goes and spends 3 seconds downloading something. If you put local models in a local database, that saves that entire step. Ka-ching is the sound you make when your application works really fast because you're using caching. And the reason that HTTP is different from most of the protocols that precede it is that URLs represent resources, not calls. And sometimes they can effectively represent calls, but they also fundamentally are resources. The URL is an address of something you can remember. So here is the HTTP cache control headers. I'm sure everybody knows all of these, what they're for, in what situations you deploy each one. And so I want to give instructions on how to implement the 11 HTTP cache control headers for precise caching. First thing is we have to understand all of the above headers, and so for the next 45 minutes, I'm going to go through all the cache headers. It's too difficult. So what I want to recommend instead is what I call good enough caching, and there's just 2 modes. Either the resource can change ever, and in that case you put this header in, or it will never change, and in that case you put this header in. That number is basically a year in seconds. And so if you get your server team to say, these resources never change, these resources do change, there's 4 lines of code in OkHttp, and suddenly caching pretty much just works. And you don't have to think about it, and you get a lot of awesome performance benefits. How do you make resources that never change? That seems kind of like an impossible task. A good example is if you have like a profile image of one of your contacts, don't give the profile image sort of like a guessable URL, like jesse.png. Instead, give it a unique random token for that particular version of that image. And then if I upload a new profile image, it just gets a new URL. So you can make it so that the URLs change, but the resources don't. You use the URL as basically a immutable identifier for that data. Compression exists, turn it on. If you use compression with JSON, it shrinks things by about 70%. gzip for responses is automatically on by default in OkHttp, but you could potentially also turn it on for requests. This requires some server support. And if you want to like totally hot rod it, you can turn on something called Brotli that gives you that extra 5%. That's if you want to be like totally elite. CDNs are content delivery networks, and they're the easiest way to improve upon speed of light. Here we are in Toronto. Most of the network calls we're making are making like calls to Silicon Valley, calls to Washington, D.C., maybe calls to Oregon, where all the different major data centers are. But when we watch our Netflix shows, those videos aren't coming to us from a server in California. They're coming to us from a server inside our ISP's data center. So if I watch like House of Cards, it's coming to me from a data center in like Waterloo. And that's because the CDNs make partnerships with ISPs, and they put your data as close as possible to the customers. And this is a really powerful strategy for making your application super fast. Your complicated backend servers can do all their JSON requests and things to your one main server, but anything like images, resources, music should just come from a CDN, and that way everything serves really, really fast, and you don't have to use your very expensive bandwidth in your data center. Also really good for availability because the bits of my Netflix shows never change, and so this dramatically changes the complexity of building big data services. Also, CDNs can do image resizing. So if you have your users upload, 12 megapixel profile pictures, and then you show them in like 200 by 200 avatar icons, don't write a whole bunch of code to do the resizing yourself. Definitely don't download the 12 megapixel image for every profile picture. Just configure your CDN to take the original image, resize it for you, and this is like 2 or 3 days worth of work, and it just makes everything really fast. Granularity, HTTP1, so there was this thing a long time ago. There's a bunch of bad advice from about 10 years ago when HTTP1 was the thing. And if you look in like an app like WhatsApp or Slack, you'll see there's like these resources. You use Charles to intercept the traffic. You'll see there's like this one image that has 500 different emojis in it. And this is something where the cost of making 500 different HTTP calls to download every emoji individually was too slow. And so the old internet would take all these different resources and smash them together into a single resource and then make the client cut and paste the right pieces out. Now that we live in the future, we have HTTP2, and we can just say, use logical resources, and HTTP2 will figure it out. The other thing that's really nice here is that with HTTP2, if we change the pixels of any one of these emojis, we invalidate just that one URL and not the entire sheet of them. Last thing is security. So this is the part where I've been ranting a lot, but now I'm really going to start ranting because the captive audience I have here, you are the ones that sit behind your profit-seeking, shareholder-benefiting corporations and the users who have very little power. And so our role as Android developers is to basically say, you know what, let's defend our users. The role of a software developer is not neutral. It's our responsibility to stand up for our users and to say, I don't think that we should build that because I think that the security cost or the privacy cost is too high. So with that in mind, let me tell you some things that you should be thinking about when you're trying to lock down your applications. Data is dangerous. If we were building applications that were holding radioactive waste or biohazards, we would be really defensive about what we're doing. And I think we should start as an industry, or continue as an industry, to start thinking of data as just something that has lots of problems. You're keeping other people's secrets when you're storing their data. And you may not think we're keeping their secrets. You may just think, we're a photo sharing app. What's so exciting about that? But as an application developer or as a product team, you don't actually know what's secret and what's not. My favorite example of this is a few years ago, Facebook had a feature where you could join a Facebook group, and you could join a Facebook group because of the church you went to or because of the board games you were interested in. And there was a college that had a Facebook group for the gay choir. And so if you wanted to sing with your friends at the gay choir at the right time, you join that Facebook group and it would tell you, we're all meeting at this time and date to sing some gay songs. The problem was that at some point, some product manager at Facebook said, we can really juice our numbers by making it so that people's group membership is public. And so, on the surface of it, it's group membership is public, but what ended up happening with this feature is they outed a bunch of their users to their family. And so you're at a gay choir and you're using it to coordinate your logistics, and then suddenly your parents are like, hey, are you homosexual? Because I'm really uncomfortable with that. And so when we're building applications, we have the ability to make these kinds of mistakes, and it's your responsibility as application developers in the field to really understand and anticipate these sorts of problems, and to be really, really thoughtful about all the potential consequences and second-order effects of what we build. The other thing is that attackers are persistent. So if you're collecting a bunch of data, 99.9% of your users have nothing interesting to hide, but some fraction of your users are holding something that could be potentially very damaging. And the attackers are not necessarily just bored high school kids. There can be nation-state attackers, and they're going to try and pull your data and do very nasty things with it. So what are the secrets? There's passwords, but there's all these additional, more obvious failures. And so advice going back to the office tomorrow is we really want to limit our exposure to data. And a good way to say is like, why are we collecting our customer's gender? Why are we collecting our customer's IP address? Do we need it? When will we delete it? When you collect a piece of data, you should think, just when can, like, this, I don't like holding this. And if you want to make a really good argument against your project managers who are in a big hurry to like do data-driven things and win the internet, you can just say, there's this thing in Europe called the GDPR, and there's this thing in California called the CCPA, and these are these like super strict, super heavy-handed privacy laws. And you can just say, you know, it's not me saying that we shouldn't collect the user's IP address, but there's this like guy in Europe called, you know, there's like this collection of people in Europe who are going to get us in big trouble if we store this data. So let's just not. And so you can use this as a really good defense. This is for us as application developers as a really easy way to push back and say, no, let's find another way to solve this. There's also this technique called differential privacy. So despite the fact that we're not necessarily collecting a lot of data on, you know, our users' IP addresses or their, you know, their zip codes or something, differential privacy allows us to still retain our ability to understand our customers, to do analytics, to say, you know, our hot demographic right now is 22 to 27-year-old moms or something. So you can still do that, but you don't have to collect individual personally identifiable information on everybody. Here's an example. So you saw this in the news a couple weeks ago. Twitter was collecting all sorts of data, but like Twitter doesn't even necessarily have control over the trustworthiness of its own employees. And this isn't unique to Twitter. This is all corporations. If you're building a company that has access to very sensitive data, big, well-funded attackers will find ways into your data center, and they will be able to collect data from your data center. And so if Twitter didn't have this data, there would have been less intention or less benefit for a nation state to spy on them. TLS is a thing. TLS is the S in HTTPS. It confirms that you're really talking to Cache App. Why do we have it? It prevents eavesdropping and it prevents interference. TLS is necessary. Every single API call you should be making should have HTTP TLS on it, but it's not sufficient. A good example is it doesn't impact what the server you're talking to does with the data once it's stored it, and it doesn't prevent URLs like cache.app.attacker.com from phishing your loved ones and taking all your money away. Old implementations of TLS had some pretty severe bugs. I don't know if you've ever tried to deal with the Canadian Revenue Agency, but they don't do email because of a TLS bug, and that's like a huge failure of our industry. And nation-state attackers do super nasty things to break TLS. There's this really stressful example. In Kazakhstan, you'd go to the internet, and your browser would say, please install this new certificate in your browser to make the internet better. And it was so that the government could man in the middle all traffic. And so this is bad. And as an application developer, like as this Kazakhstan government was basically running the Charles Proxy app I just showed you, but on every single one of their citizens. And that was uncool. So as developers, one of the threat vectors that we have to deal with in 2019 is nation-state attacks. There's a thing called a certificate authority, and it's just a company like VeriSign that confirms that the website is owned by who they say it is. And your browser trusts about 300 different certificate authorities, and an attacker like the government of Iran or the government of Kazakhstan potentially just needs to compromise one of these certificate authorities to break into all of your applications. And these are just like normal dysfunctional companies like every company. And so there's 300 of them. Any sort of mistake, somebody at one of these companies gets phished, and we're in deep trouble. And like I said, Kazakhstan tried to add themselves to the browser. So another example is 10 years ago, the government of Iran compromised a certificate authority in the Netherlands, and then they used the Netherlands certificate authority to man in the middle all of the Iranian internet traffic. And this is so that they can crack down on dissidents and journalists. And as application developers, you know, our data, we are carrying the data that these people are trusting us with. So how do we defend ourselves against the very well-funded governments of these major countries? There's one technology called certificate pinning, and the easiest way to think of it is it just limits which of the 300 certificate authorities you trust. And here's another 5-line example of OkHttp. And you have to get those codes from your certificates. Once you have those codes, it just prevents Iran or Kazakhstan or Saudi Arabia from being able to intercept traffic between your users and your servers. There's a bunch of different versions of TLS. The most recent is brand new, called TLS 1.3, and it is great. This one's dead, this one's dead. This one's gonna die in January. This has caused a lot of Android developers a lot of heartache, especially me, because I said, earlier this year, I said, OkHttp is no longer supporting Android 4.4, and that impacts a ton of users that are on devices that don't have TLS 1.2. So if you're currently supporting Android 4.4, you're pinned on an old version of OkHttp, and that's fine. You can use that version as long as you need to. At some point soon, we're hoping that these devices age out and users get new devices that have new TLS tech. Android 5. Oh, and you can also retroactively get TLS 1.2 on Android 4.4 devices. It's a big pain. I'd prefer you not have to. Last kind of attacker is the attacker like me who is just using Charles to intercept traffic. I can go in and not only take like my to-do list applications traffic, but I can take your banking application or something and try to understand how it works, and then make HTTP calls against your server in nasty ways. And I like to think of it as like our applications are instruction manuals for reverse engineers. They show what the network requests do, and they show what the consequences of them are. And there are these awesome tools that make it like really, really easy. One of them is called Objection, and you basically get this command line app and you say, disable SSL pinning, that's the certificate pinning we just showed, and it will turn certificate pinning off for my device. And so if I want to man in the middle my own device, this lets me do it, and that way I can intercept my own traffic and understand what's going on. How do we defend against these things? Not really possible. A sufficiently determined attacker will reverse engineer your protocol and take your keys for your kingdom. Well, not take the keys for your kingdom, but be able to manipulate traffic and potentially spoof and spam your network. And so what we do is just make it really annoying. And one of the things we're thinking about doing on my team is adding an HTTP header that will just annoy hackers because they will have to figure out what the thing they have to hash is to get that value. That's the depressing security section. All right, last bit is like the optimistic outlook of the new things I'm excited about, like an arena of dinosaurs fighting. So there's this thing called Envoy that feels like really technology from the future, and the elevator pitch of Envoy is that Middleboxes are like so 2000 and late, and so what we want instead are sideboxes. And here's a diagram of this. We got our pizza app and our pizza server, and then we like put Envoy here. And if I say like, order a pepperoni pizza, I make an HTTP request from my device to the Envoy proxy that's running on my device. It makes an HTTP request to the Envoy proxy that's running on the server, and then that program makes an HTTP request to the Envoy or to the HTTP server process itself. And so every HTTP call in an Envoy universe goes from being one HTTP network request to being 3. And this is something that's like a massive waste of CO2 and electrons and server bills, but it's also incredibly powerful because now we can change routing things client-side. And so Middleboxes are difficult to scale, they're difficult to maintain, and Envoy basically says we don't need Middleboxes, we just need really, really smart sideboxes. So this is something that is coming and cool. There's also this thing that we may have heard a little bit about called HTTP 3. We just got HTTP 2. I'm so sick of learning about new HTTPs. The benefit of HTTP 3 is better worst case latency, and this is neat. You can change your IP address without restarting a download. So you're at home and you start watching, the new, there's a new live action version of Lady and the Tramp on Disney+. You start watching that. And you start on your home Wi-Fi network, and then you leave home and you go onto like your cell phone carrier's 4G network, and then you get on like the TTC or something with Wi-Fi, the light rail, and it has a Wi-Fi network, and then you go off of that into your office, again through another network transition, and you were on 4 different IP addresses in this process. And with HTTP 3, the download never stalls. It's the same exact download, and you can carry you from one IP address to the next. This is like really cool, really powerful, futuristic stuff. Who wants their movie to pause while they're watching a movie on the commute to work? Not me. The way HTTP 1 was structured was we have TCP packets at the base layer. On top of that, we take each packet and we build a stream abstraction on top of it. And then we layer on our requests and responses on top of that stream abstraction. With TLS, we just add another layer in the middle, which is the TLS streams. So our basic TCP streams are not encrypted, and then we add encrypted streams. And then on top of that, we have our requests and responses. With HTTP 2, the idea was the TLS layer was the bottom layer that anybody was interested in working on. So you retain the same 3 layers at the bottom. But then you say, we want to multiplex. We want to send multiple different streams all concurrently. And so you end up with like a different kind of like packeting layer called HTTP2 frames. And so this allows you to deliver fragments of different streams all on a single enclosing stream. And so HTTP2, the architecture or the structure of it is a little bit redundant because we have 2 different sort of like packet layers. We have the base TCP packets, and then we have these HTTP2 frames that serve a very similar purpose. And so with HTTP 3, it's like a fundamental refactoring of where we found ourselves. And so what it does is it starts with UDP packets. It adds quick streams, which combine sort of like the utility of TCP streams and the utility of TLS streams. And then the requests and responses are layered on top of that. And so this is a really big refactoring, restructuring of how these protocols are layered. It's a little bit less elegant because quick streams just do so much. But it's also a lot more capable because if you lose any of the TCP packets at the bottom layer, you sort of stall the entire call. Whereas with HTTP 3, if you lose any individual packets, the rest of everything stays really healthy. So it's coming. It's incredibly complex. It's far more complicated than any of the protocols that preceded it. But it's also really powerful. And again, not having to restart that Lady in the Tramp download is going to be awesome. I work on this service called MISC. It's kind of like Spring Boot or Ktor. The question we're trying to answer with MISC is, what if we built a server framework that worked like Retrofit? And it's got interceptors and annotations and all the sort of powerful retrofitty things. It combines gRPC and REST in one framework, but MISC is like very, very, very before. We're very, very early. We're not at all near 1.0. But it's something I'm really excited about. This is where I'm spending a lot of my days building this cool framework. And then the last thing I want to talk about is this library OkHttp. Hopefully lots of you are using it. We're currently working on new concurrency internals. So the number of threads OkHttp uses internally to satisfy your request is going to go down. We're going to try and make it the fastest HTTP client. I think we might already be there, but we want to measure it. And new features we're looking at is async IO and coroutines. So OkHttp has there's lots of work for us to do still. So that is HTTP in a hostile world. Thanks, everybody. Enjoy droidconTO.